So as I mentioned, the purpose of this webinar series, this topic today, and what we're going to do in the upcoming weeks is to just talk a little bit about how machine learning functions in applications for AIOps, which of course stands for artificial intelligence for IT operations. There's not a ton of artificial intelligence going down in IT operations these days. Most of it is machine learning. There's a lot of more AI going on in kind of the image and language processing space for things like chatbots. We'll get around to that at some point in the future too, but today we're going to focus on some very, very robust and old school regression techniques that work really, really well for IT data. So just to remind you about AIOps, this is Gartner's term, which has taken over the industry, and it's kind of a buzzword, but the net of it is that what Gartner suggests and what we at BMC believe also is it's time to break down the siloed approach, not necessarily from a practice perspective, but from a data perspective between your management of your IT and your servicing of the IT. So the idea is that your data that's coming in through your performance monitoring tools and your data that's coming in through your ticketing tools, you want to bring that together in a consolidated data platform, which you see there represented in the middle of the circle, the second layer out called big data. And then you're going to have this huge volume of digital data, machine data, user data, and so on. It's too big at scale for human beings to manage, so you need to get the machines involved. And what we're going to talk about today is that dot in the middle around machine learning. So first off, let me set some goals for the session. The first thing we're going to do is we're going to define what machine learning is, so you guys have a baseline of what that is. We're going to talk about the difference between supervised and unsupervised, because I think that causes a lot of confusion, and talk about what that means for today. We're going to cover 3 different kinds of regression techniques. I'm going to show you some visualizations, and we're going to talk through how they get calculated so you can understand the mechanics of them. Then we're going to talk about how you evaluate the performance of different regression techniques and how you would determine whether they're good or bad. Well, determine how good or how bad they are, I should say. And then we'll talk a little bit about just AIOps applications. As a bonus, this is a picture of me last December when I was in Cambridge, and I visited the Harvard philosophy department. My background's actually in philosophy in academia, and I'm standing outside of Amartya Sen's office at Harvard. You can click on the link here in the presentation when I share it, or you can Google him right now. He's a pretty famous and important dude, won a Nobel Prize. So it was pretty fun for me. All right, what is machine learning? So this is the definition. If you go and you look online, you go to Wikipedia or something like that, this is what you're going to see. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. If its performance of task T is measured by P, improves with the experience E. I don't think that's particularly helpful in layman's terms, so I found this other definition that I like better, and it's this. Really what it does is machine learning means the system can learn and improve from experience without you having to explicitly tell it. So I think that's, to me, the most concise and simple way to put it, is you release the machine on your data, and based on what it sees in the data and what it knows, it learns from the data and it improves the way that it does its job without you having to go in and tune it. Which leads into the next topic, talking about supervised versus unsupervised machine learning. So there are, I feel like these terms, they're a little misleading. This really, I would say trained, I use the term trained and untrained, but essentially supervised means that you're giving the machine some sample data first before you release it into the wild, and you have a sample set of data where you know what you're looking for. So you can tell the machine, I'm giving you A, I want you to find B, and what the machine does then is it connects the dots and it creates the model that gets from A to B. Then what you can do is you can give it new data, just give it new data, new types of A, or new iterations on the data type of A, and it will predict what the outcome is based on that algorithm that it's created, right? So you're training the machine on data that you have that you know what it's supposed to look like. That's what supervision is. Unsupervised means you don't know necessarily what the outcome is that you're looking for. you're looking for the machine to go in and to uncover structures inside the data that you're not aware of. So you're not giving it any expected outcome. You're not training it. You're just going ahead and putting it right on the data itself. That's the difference. And these are not hierarchical. It's not like you move from supervised to unsupervised necessarily or what have you. They're different techniques for different types of data to solve different problems. And that's a theme you're going to hear frequently from me, is that the techniques that you use to solve IT problems depend heavily on the data and the specific problem you're trying to solve. And you might have multiple ways of going after that, but not every technique is going to apply to every type of problem and every type of data. All right, so the last piece here is just to let you know that everything we're talking about today is supervised. That's the way regression works, or at least the types I'm talking about. So you should just keep that in mind, that it's all going to be supervised examples. All right, so let's get into the meat of it. Regression. What are we regressing towards? What does regression mean? So regression is a technique to look at a set of data and then to calculate a model that regresses or reverts, sometimes the term you might hear, towards the mean. So we'll talk about what mean means in a second, but essentially what you're doing is you're saying you're giving a dependent variable or a set of, you're given a dependent variable that you're trying to predict. This is what you want to know. You want this as an output, a single output, right? So for example, you want to predict when CPU and memory usage are combined hit a certain threshold, then what does that do for my input-output on my web apps, something like that, right? So your output is what you want to find out, and then your inputs are the variables that contribute to producing that output variable. So dependent and output, independent and input. And you can have one input variable. You can just do a single one-to-one mapping. So you have one input variable and you're predicting one output. Or you might have a whole set of independent variables. You can have 2, 3, 4, 100 different variables that all contribute to that single output variable. And basically what regression does is it looks at what the output, what you're trying to get. It looks at the input and it produces what is called a best fit model. So it's a mathematical representation of the best, essentially what fits the data the best in the mean, so to speak, between all the data points that you have. And then it uses that to predict new output data when you provide it new input data. Now, the important thing to remember about this, and when we get into the visualizations, hopefully this will make more sense, is that this relationship of regression shows correlation. It does not show causation. So it's a predictive capability, but you can't say necessarily that you have a causal relationship in play. It's just strictly correlation. All right, so when does this work? This works when you have some kind of distribution in your data that makes sense. You look at the data and it looks linear or it looks grouped in certain ways that are applicable. You might have some outliers, but you do have some kind of distribution. There's another way of saying it is that you don't have a random distribution, right? There's definitely a non-random distribution of your data, and you have some data that you know both the independent, aka the input, as well as the dependent in the output that you can use to train the system. If you don't have existing data, you cannot use regression. I've got a picture there of Sir Francis Galton on the right. He's the person who essentially invented the regression technique, I think back in about 1862 or something like that. So it's been around for quite some time. All right, so let's start with the easiest form of regression. It's called simple linear regression. And this is called simple because it's when you have just one independent variable, right? And you have one output variable, one independent input variable, and you have a distribution of your data that suggests that there's a straight line relationship. So if you look over on the left, this is some data that I grabbed off the internet, just some random data that's meant to simulate a roughly simple linear regression data set. Now, the way that the algorithm works, if you look over on the right-hand side, is it looks at all of the data points in your data set, and then it hypothesizes, so to speak, a line that runs somewhere in the middle of your data, the mean. It then calculates, and this is not exactly how it works, I'm just trying to explain it to you. It calculates the distance between each one of the points in your data set and that hypothetical line that runs roughly through the middle of the data set. So that's represented on the right by the red dashed lines. So you see there's the first point on the lower left is, kind of one dash away from the green line, which is our model line. The next one is about the same distance away, maybe a little closer. The third point is quite a bit further away. The fourth point's a little bit less than that, so on and so forth, right? So what the algorithm does is it calculates the distance represented by those red dotted lines for each one of the data points, and it squares each one of those and adds them together. And then what it's looking for is it's looking to find the minimum number of the sum of all of those squared distances. So it's trying to minimize the amount of distance, as it were, of all the points from the line. And whichever line satisfies that, it has the line that it puts in has the smallest distance from all the points cumulatively, or the distance of all the points squared cumulatively, then that becomes your actual linear regression line. So if we look at it in our existing data set here, by the way, the graph on the left I did in Excel. This is just Excel's linear function. If you right-click on your data set in Excel and you ask for add a trend line, you'll see it pops up a window and you've got linear and polynomial and logarithmic. This is just the linear trend line that Excel puts in the data. So what you have once you have a line then is you can see if I give you a new data point, let's call it A, right, for my independent variable X, if I give you a data point of A, like let's say over looking at our graph on the left, let's say I told you my input was 85, right, then what the model is going to do is it essentially, you can imagine a straight line up from your x-axis, which is your independent variable, where you hit the line as it shows on the chart. You go straight over horizontally to the left over to your y-axis, and that's the predicted outcome. And that's basically how simple linear regression works. It creates a line through your data that essentially minimizes the distribution, the distance, as it were, of all those points from the line itself, and that's how it gets there. Now, a couple of things that are, for those of you who took algebra, either recently or a long time ago in school, the first thing is the reason that it sums the squares as opposed to just the distances is you have positive and negative distance. If you think of positive as higher than the line and negative as lower than the line, when you square your numbers, then you eliminate the negative and positive so that you get a full standardized set of data. And when you add it up, it adds up the same no matter which line you're looking at. So that's the first thing. And then the fun fact is the equation for that line is represented in this way. Y equals beta sub 0 plus beta sub 1 times x. Now, for those of you who took algebra, this might be familiar. If you remember y equals mx plus b, right? Y equals mx, where m is the slope and b is the intercept. It is the same equation. So you can still represent where this line intercepts the y-axis, or the x-axis, and then what the slope is. It's essentially the same thing. All right. So let's go on then to the next thing, which is multiple linear regression. So multiple linear regression hopefully is pretty obvious based on single linear regression. It's simply the same concept, but where you have more than one independent variable, more than one input variable. So I did my best to give you a representation in 3 dimensions using my very poor graphical skills here. But I think you get the idea that, and this, by the way, this is as many as we can represent visually because our human brains are really only able to see in 3 dimensions. But there are mathematical ways to represent 3 and more variables. It's the same concept. It works the same way mathematically. We just don't have a way to show it on the screen quite like this. There are techniques that statisticians and data scientists use to boil down multiple variables into a visual representation, but we're not going to do that here. I just want to make the point here. So we have the same concept where we're looking at the distance between the points and a representation of the mean, except in this case, instead of a line, it's going to be a plane. It's what's called a hyperplane. So analogous to what we just talked about with simple linear regression, you have a spread in 3 dimensions as opposed to 2 dimensions because we have 2 independent variables here. And instead of a line, you're going to calculate a plane that does the same thing. It minimizes the difference, the distance rather, between the points and your model plane, trying to square each one individually, you add them up and you find the one that has the minimum, and that's the best fit for this particular data set. And it would work in essentially the same way. So you'd have a plane going through your data on the left, something like that, and then you'd have a similar kind of predictive capability, only in this case, instead of just giving one, like, where I told you before, yes, in the last example, if you give me a value of A, I predict B. In this case, I need two input variables, X1 and X2. So you give me A and B, and then I predict C. And it's the same concept if you think of it in physical space where you're going to go out away from the X1 axis, out away from the X2 axis. On those dotted black lines where they intersect, you're going to go straight up to the plane, and then you go straight over from the plane to your y-axis, and that gives you your output. Now, what's interesting, just also to show you the equation, it is a very, very similar to this. Well, I should say this. You can see that it's an iteration, so to speak, on the simple linear regression where all you're doing is you're adding incremental variables in the form of your beta sub 2 times x2 plus, dot, 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 all the way out to beta sub n times xn. For those of you who don't know that notation, dot, 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 plus, and then you have, sub n or n to the nth, something like that, just means for however many you have. N is however many you happen to have. So if it's 20, the equation would be, x1, it would be the beta sub 1 times x1 plus beta sub 2 times x2 plus beta sub 3 times x3 all the way up to 20. If it was 50, it would be up to 50. If it was 7, it would be up to 7. And that n just represents however far you have to go for that particular equation. All right, so straight lines are great, but what happens if you've got curves? Well, again, usually visually you can tell very visually whether you've got a straight line or a curved line relationship. And we have a different type of regression that's called polynomial regression, which we use when we have curved relationship. So what this basically does is it changes the formula from being multiplicative to having an exponent. So I actually see there's an error in my formula down on the right, so I apologize for that. But what you'll see is instead of b sub 1 times x sub 1 plus b sub 2 times x sub 2 plus b sub 3 times x sub 3, the calculation works this way. It goes b sub 1 times x sub 1 plus b sub 2 times x sub 1 squared, then b sub 3 times x sub 1 cubed, and so on and so forth. And what that does, that's just the mathematical process, but what that does is it allows you to introduce the notion of curvature into your predictive line. So in this example, we're looking over here on the left. You can see, just looking at the data, you can tell that that a straight line is not going to fit the data very well. And again, what you do then is you can use this polynomial regression technique. It's a different calculation. Same concept. You're still trying to calculate the distance of the dots from your hypothetical line and minimize that. It's still the same process, but you're using a different mathematical formula that allows you to introduce curvature into your line instead of just a straight line mathematical formula. Okay, so hopefully at this point you've got a pretty clear sense of these very simple regression techniques that are very robust, right? So let's talk about how you tell whether they're any good or how well they're working, we should say. Well, so first off, just like we looked at when we looked at those graphs in the previous screens, you can split your data that you're using to train the system into two sets. You'd create a training set and a test set, right? This is the supervisory aspect. So you can take a subset of your data, you apply the regression technique, you output a model, then you take a fresh new set of data from that same, another different subset from that same data set, you apply the calculation to it, and if it looks like it fits well, like visually, if you can visualize it and it looks like it fits well, great, you have some visual confirmation. And that's not unusual. There's nothing illegitimate about using visual confirmation where it makes sense. But there are some mathematical calculations that you can do as well, which allow you to determine what's called the goodness of fit. So I'm just going to talk very briefly about these. I will tell you that for $12 US, you can get on, Udemy or one of these other, learning academies online, and you can get hours and hours and hours of training on all these topics, and if you want to dive deeper into them. But the first mathematical way of evaluating the performance of the model for single independent variables, this works for, just when you have a one in, one out type model, is called R squared. And R squared is really, if you boil it down, it's a representation of the difference between the line that you modeled, that your regression determined as the minimum distance between all the points in the line, versus just a straight up average line. So, and an average line here means if you take, for example, that first data set we looked at with the roughly straight line, if I added up all those points, if I added up the y value of all those points, and then I divided by the total number of those points, I'd get an average, which in the case of that data set would have been about 50. And if you just drew a straight horizontal line on the graph across the level of 50, that's your average line. So R squared essentially represents the difference between the line that we calculated in the data versus that average line, right? And so it's basically a representation. R squared is a representation of how good your model is compared to an average, which is to say compared to doing no regression whatsoever. That, like, just doing the simplest, if you just took an average, which is the easiest thing to do with your data set and you were trying to predict, it tells you how different it is from the average, right? And so that in itself may or may not be useful information for you, but it does provide a reference point. So if you have to compare different models against each other, you can use R squared to compare their difference from the average, and then you can tell whether one is a better fit or a worse fit, right? Essentially giving you a reference point for comparing different models where you wouldn't have if you didn't have a way to calculate the goodness of fit. Now, there is a more complicated mathematical evaluation called adjusted R squared, and that is for when you have more than one independent variable. And all this does is it adds in some additional information into the equation that lets you know that as you add more variables, whether you're improving the accuracy of your model or if you're adding unnecessary complexity without improving it, or in fact hurting the model. And there's some weird math stuff in there for why you need to do adjusted R squared to figure this out, but essentially this is useful because when you have a multiple linear regression where you have multiple input independent variables contributing, let's say you have 10, it may be that only 5 of them have any really meaningful statistical significance on your prediction, and you don't want to calculate the 5 that don't have any input on there. So there's this adjusted R-squared gives you a method for, as you consider additional variables in your model, it tells you whether you can use them or if you can get rid of them, essentially, and simplify and boil down to just the important ones that are relevant to your prediction. All right. So let's now talk about what we've learned here so far. The first is we've established that we now have some machine learning techniques, simple linear regression, multiple linear regression, and polynomial regression, which are very closely related. And they give us the ability to create models for straight and curved line relationships, right, visually, if you think of them that way, between one or more independent variables and a dependent variable we'd like to predict. And this seems very simple, and you say, well, you know, how much utility does something this simple have? And I'm really interested in all the complex, interesting stuff. Well, anybody who's been in IT operations for any period of time knows that the vast majority of IT performance data, particularly performance management data that's collected, fits this model, or it's essentially you can represent all kinds of telemetry out of IT systems in terms of curvilinear or straight lines, or a mixture, right? And we'll talk about time series at some point. That's another big part of IT operations. But we have so much data in IT operations that fits this profile. We don't need fancy gymnastics. We don't need artificial intelligence. We don't need a lot of heavy lifting to get a lot of value out of machine learning in these contexts. So just let's talk about 3 simple examples. One that we know a lot about here at BMC, but that's very important in the industry, is thinking in terms of less about capacity forecasting. This is true for any resource that you consume. Understanding saturation points, understanding consumption points, understanding managing quotas, and this. So if you look at that example in the upper left, this is actually a screenshot from our capacity optimization tool, but essentially, this is a mapping using a very simple linear regression model of looking at a series or a total number of events, and then predicting what CPU utilization will be like. And that red zone on the right tells you, right, okay, when you hit this many events, you are going to be hitting a saturation point on your CPU where you might experience the need to add additional resources or what have you, right? Now, capacity forecasting involves a lot more than just simple linear regression, and what I mean by that is when you operationalize these techniques and you put them into tools where you're managing in constant influx of data and very complex systems or whatever, there's some extra work you have to do, but at heart, doing a regression technique, a linear regression is what's at work in doing your capacity forecasting. Now, that gets really powerful if you can pair your forecasting capability with things like application and service models, business impact, those sorts of things. So if you imagine having the capability to apply your regression techniques and forecast the usage and the impact of various types of variables, like, say, total events, total users, API calls, whatever the case may be, do regression analysis and understand the impact on things like CPU, memory, disk I/O, whatever, network saturation, so forth, and then map that to a service model or a business impact model or an application model, then what you get is you get the ability to actually predict outage or performance degradation, right? And you can connect the dots and connect the 2 pieces together. So it's really, you can essentially tell the system can learn not just about doing the regression analysis to understand the time or the set of variables that are going to lead to the impact, but then it can actually understand the impact itself by virtue of the topology and the relationships that you're feeding it in your with your model, your application model, or your service model. Another example of using regression in a very simple but useful way is predicting costs. This can be, I'm using this here as cloud costs because it's a very common use case right now and a very important one. But essentially, you can use regression techniques to look at your usage of particular cloud services, right? So at AWS, there's EC2, there's S3, there's Lambda, there's a million ECR, there's a million different services in AWS, and you have a billing API which provides, which can be your, another input independent variable that you put into the system. You understand your billing costs, and then you can look at your total cost as an output that you want to predict, and you can use regression models to look at all the resources you're consuming, how much they're consuming, who's consuming them, where they're coming from. You can then predict what your costs are going to be based on the trend, based on where the consumption is going. And then you can actually, again, when you pair that with a budgeting capability or feature, then you can start actually managing budgets for your cloud resources. Again, all of this is using some relatively robust but straightforward regression techniques at heart, combined with some other algorithms to pull the data together and represent it to you in visual formats and so forth. But these are just three very simple examples. These are very simple examples of how regression functions to provide value for AIOps, right? To put machine learning into practice for IT operations. These three things are real in not just they're real in BMC products, they're real in other products, but these are very, this is not science fiction. It's happening right now today. I'd be happy to share other examples when I post this stuff out on communities. I'll be happy to share. If you guys got questions, you want to understand other things, we can certainly go through and maybe deep dive on some of these examples and talk about how they actually work. All right, so some other topics that I'm planning on bringing up in the future. We can talk about some other forms of regression. I probably will put off some of these to get into classification where I think they're more interesting, but there's other techniques. It's just different mathematical formulas underneath. One's called support vector. Decision tree is a very common and heavily used. It can be used for regression or classification. And so that would be one that I think I'll save for classification. And then you have logistic regression, which is where you look at data to produce a judgment about a binary output. So, for example, logistic regression is used when you want to determine if something is A or not A. So it looks at mail. Your mail system uses logistic regression possibly to determine if something is spam or not spam. Is it a threat or not a threat? Is it an anomaly or not an anomaly, right? The regression we looked at gives you a predicted output on a continuum, like a potentially infinite number of variables, but a continuous one. Logistic regression is used to just predict A or not A, or A or B, or A or B or C, something like that. All right, so I talked about classification. We're going to talk about that. Classification is great for events and logs. Same with clustering. Classification is a supervised learning technique, training technique. Clustering can be used as unsupervised, so we'll talk about that. We'll talk about natural language processing. We can do a session on that and talk about how natural language processing works for taking unstructured data and parsing it into various types of clusters, groups, pairings, what have you. We'll talk about ANOVA, which is the predominant algorithm for looking at time series data. And then, we can get into some topics around, for example, like neural networks, deep learning, some of the fancier stuff, which in a lot of respects are just refinements and improvements on the techniques that I just showed you today, right? And there are more sophisticated ways to calculate, which give you the ability to handle more sophisticated data sets, but ultimately you're just, it's a better mousetrap in a lot of respects, as long as you're continuing to do this basic supervised or unsupervised machine learning type activity. All right, I'm going to leave you with this. This is just some sample TrueSight AIOps use cases, and I've listed out here the different types of machine learning and algorithms and techniques that we use to make all this stuff happen. Where, like I said, we can go into, we'll talk about classification, we can go into all these in some future sessions. But I wanted to stop here. Let me end my show and bring WebEx back up. So I hope, let's see, people are still connected. Let me stop sharing and see. All right. Let me take a look and see if anybody's still on. Yes, we still have 20 people. And we've got some questions. Let me go ahead and answer them. All right, so Jamil asks, is dynamic baselining TrueSight an example of your AIOps? Yes, it is. We did a session last year where we talked through how dynamic baselining works in practice. That is a combination of doing regression as well as that ANOVA time series technique, as well as seasonal decomposition and things like that, Jamil. So it's a combination of techniques, but essentially what it does is it learns from, let's just take one metric, for example, like CPU. It looks at the past performance of the CPU and it creates a model for the expected future performance of the CPU. It takes into account variation. So for example, time of day, day of week, week of month, so on. And then it predicts the future performance of that particular metric, and it adds a band, basically an error, plus and minus error to put a bandwidth around it. So it's basically telling you, it doesn't predict, a specific like 95% at this day at this time. It predicts a band between, let's say, 90 and 100% that it expects to find the metric in that time series. So yes, dynamic baselining is an example of AIOps. All right, Jamil also asks, is probable cause analysis also an example of AIOps? The answer is yes. So probable cause analysis uses different techniques. It does use, there is some regression, but it also uses classification. Basically, probable cause analysis, for those of you who aren't aware, is probable cause analysis, if you take an event and you run a probable cause analysis against that event, if you have brought in performance metrics in the form of telemetry, events in the, through your event management console and logs, it can look at all three of those things, and based on the timestamp and the service model and correlation and data inside the events and logs themselves, plus the metrics, it puts all that together and it calculates a probability of causal relationship between other events or other metrics and the event that you observed. So it is an example of how we use algorithms and machine learning to for AIOps in that sense. Probable cause is. We should probably do a session where we just dig into how that actually works. And yes, TrueSight does have the ability to do predictive alerting. So, once you set up dynamic baselining and you've got, you can enable predictive alerting, and what that will do is, based on the baseline that is measured, the system can look at the current trend on a particular metric and predict if it's going to go outside of expectations and give you a predictive warning. We have that capability. All right. Volker asks, what are some of the dependencies you recommend to be covered before starting with AIOps? So Volker, that's a pretty good broad question. I've written some blog posts on this topic. As you know, if you're talking about knowledge, the level of knowledge that I'm trying to represent in something like this session is, I think, sufficient for an IT operator to understand some of the basic concepts behind AIOps so that they can make informed decisions about how to leverage the systems, how to talk to vendors, about what the systems do and what the expectations are. But from an operational perspective, there are quite a number of other pretty significant dependencies, and one of them is at the data layer. So one thing that I counsel customers on when we talk about AIOps is you have got to understand what data you have from all your various systems that you want to start bringing into the conversation with each other. You need to understand where that data is, what that data looks like, how to get that data free from where it is, either directly from the system that it sits in or to offload it into a big data platform that you can then use for analytics. And you need to understand the frequency with which you can do that. That's like a basic, just having a basic foundation of understanding what you have to work with. And so it's one of the things that we see when we talk to customers about working with other solutions. And our solution is, one of the great things about TrueSight as a platform is we already have the ability to collect and aggregate tons of data from tons of different sources, right? Because we've been doing this for so long, and we modernize and keep up with the newest system. So, for example, we have the ability, we have an event data store in TrueSight already. We have a log data store in TrueSight. We have a performance data store in TrueSight. And we're looking to modernize that back end to make it more performance ready for real-time analytics. But, if you're working with, somebody besides BNC, you've got performance metrics in 20 different monitoring tools. You've got events coming from 50 different systems. You've got logs coming from all over. One of the first things you have to do before you can start thinking about AIOps is figure out how you're going to bring all that data together, what that looks like. And that's a huge prerequisite. All right, so it looks like Jamil had some more information. He and I, it looks like we'll have a conversation about probable cause. Perhaps we have that offline. And Hamid says, why have you not disclosed that you're a mathematician and a philosopher at the same time? Well, probably because I think I can reasonably lay claim to being a philosopher, but I don't know if I can lay claim to being a mathematician. So just so you guys know, I did get my master's degree in philosophy before I got into IT. And I have a philosophy podcast that I do with some friends of mine from grad school called The Partially Examined Life. We've been doing it for 10 years. So I feel like I have some credibility as a philosopher. But I can tell you that everything that I just showed you today, I learned myself by teaching myself from resources that are freely or cheaply available on the web, from universities, that sort of thing. And I think, what's great about where we live, kind of the time we live in right now, is there's just a wealth of knowledge available and the self-education resources available for people like us, IT operators, IT professionals, to educate ourselves about where the market's going. And, if you're willing to put in 5 or 10 hours worth of work, you can develop skills that will allow you to think, basically transition to the future as we move to these AIOps platforms. And that's another conversation that I do have with customers, is I really believe that the future of IT operations is as auditors, not as doers. So I believe that, as the systems get smarter, as data starts moving faster through the system, as analytics become more sophisticated, as machine learning becomes more ubiquitous, the IT operator and IT folks are going to need to understand how those systems work and become auditors and managers of those systems, as opposed to, executing, putting workflows into place, that kind of thing. So this represents me trying to do that for myself, and I highly encourage all of you to do the same.